Welcome back to our videos. Now we're in chapter 2. This is section 2.1, derivatives and the rate of change. So we're beginning to get into the concept of derivatives in calculus. But a little background, you guys should be familiar with the idea of slope. And the idea of slope is rise over run, or change in y over change in x. Formula is y2 minus y1 over x2 minus x1, where you would have a couple of points, x1, y1, and x2, y2. Now, what we're interested in is the slope of a secant line. Now, all a secant line really is you happen to have a function where you had 2 points on there. So what's new is you have to have this function, but you still have 2 points on a particular function f of x. We're still going to call them the first point x1, y1, the second point is x2, y2, and we're going to find the equation of the line that connects these 2 points together on the particular function. So the formula for the slope of the secant line is, it's the same old slope, m equals y2 minus y1 over x2 minus x1, but since these are points on a function, it's also going to be known as m equals f of x2 minus f of x1 divided by x2 minus x1. So an example, find the slope of a secant line where f of x is equal to x squared plus 3x minus 5. Between the points x equals 1 and x equals 2. So to find the slope, m, this would be equal to f of your second point, which x coordinate is 2, minus f of the x coordinate of the first point, which is 1, divided by 2 minus 1. Now the next thing we got to find is what is f of 2 going to be. Now they gave me f of x. f of x is x squared plus 3x minus 5. So what we're going to do is plug in 2. This would be 2 squared plus 3 times 2 minus 5. That's equal to 4 plus 6 minus 5, which equals 5. And we need to calculate f of 1 to plug in here. F of 1 would be 1 squared plus 3 times 1 minus 5, which is 1 plus 3 minus 5, which equals, that's 4 minus 5 is negative 1. So now, plug these numbers into my slope formula here. F2 is 5 minus F1 is negative 1 divided by 2 minus 1. And when we clean this up, we end up getting 5 plus 1, which equals 6, over 2 minus 1, which is 6 over 1 equals 6. So there is my slope of my secant line. And again, all a secant line is a line that connects 2 points on a given particular function. Now look at part B on this one. Now we want to find the equation of the secant line of the function f of x equals x squared plus 3x minus 5 between the points 1 and 2. So it's the same problem here, but now we want to find the equation of a secant line. Whether it's a secant line or any other kind of line, anytime you need to find the equation of a line, you want to use the point slope formula for coming up with lines. Point slope formula. That point slope formula is y minus y1 equals m times x minus x1. And you got to have two things to use the point slope formula. You've got to have a point and a slope. So all you need is 1 point. Well, to have a point, you have an x and a y coordinate. Now, we got 2 x coordinates, so I need an actual point. So I'm going to pick the smallest one, the smallest x coordinate, 1, and I need the y coordinate. But up here, we found the y coordinate. When I plugged in 1 into my function, I got negative 1. So there's my point. And now my slope of my secant line, the slope of the line, which we calculated up here, it was equal to 6. So now I have a point slope, plug it in. Y minus the y coordinate, negative 1, equals a slope of 6 times x minus x1. X minus the x coordinate, negative 1. Now x minus positive 1 there. Now I wrote this in a certain way because I wanted you to see me literally plug numbers into my formula. Now let's clean this guy up. So y minus negative 1 is y plus 1. That's equal to 6 times x minus 1. Now I'm going to distribute. Y plus 1 equals 6x minus 6. Subtract 1 from both sides, and this gives me y equals 6x minus 7. And this is in what we call slope-intercept form, the old y equals mx plus b format. But this is my equation on my line. Y equals 6x minus 7. The slope is 6, the y-intercept is negative 7, but that's what they wanted me to find. Now, continuing on, now if we take this slope of a secant line to an extreme, we're going to get something called the definition of derivative. The definition of derivative that your professor is going to be going over in class is this idea of, okay, you have a slope of a secant line between 2 points. Okay, so here's my function right up here, and I happen to have a point x and a different point called x plus h over a little bit, and we found this slope of the secant line that connects these 2 points. But what we're after here is this, something called the slope of the tangent line. To turn this into the slope of a tangent line, we're interested in actually having the particular slope at just 1 point. This is a tangent line. So to create this slope of a tangent line, what you do here is you make the distance between x and that x plus a little bit, that x plus h, make that distance h go to 0, and that introduces the concept of limits. So you pull this point all the way back to this guy, and what you end up getting is the slope of the tangent line. And by formula, the derivative is the slope of a tangent line. So in our textbook, we came up with 2 different ways of calculating the slope of a tangent line. We got f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. But another way we could calculate this derivative is f prime of a is a particular point that you want to plug in, which is equal to the limit as x approaches a of f of x minus f of a over x minus a. Both these 2 guys are going to give you this slope of the tangent line. This is usually used to calculate a formula for the slope of the tangent line based upon x. This one will actually give you a numerical value for a slope of a tangent line when x actually equals a. And this notation, f prime of a, is the notation for the derivative which gives you the slope of the tangent line at a. So we're going to denote this as the function, whatever we're given with, prime. That's a classic Newtonian notation here. Now, so let's take a look at this, a couple of examples here. Find the equation of the tangent line of the function f of x equals x squared plus 3x plus 10, where x is equal to 5. All right, so I'm going to do this in a couple of different ways. So this one right here, the equation of a tangent line. But anytime you need to find an equation of a line, you're going to use the point-slope formula. You need a point and a slope. But this is real in particular very important when we're on a tangent line. And the slope of a tangent line is known as the derivative. And we want the derivative of f when x equals 5, so at 5. So this is what we're after. So I'm going to use this formula right up here. F prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a, where my a is going to be 5. So when I plug that in, this will be the limit as x approaches 5 of f of x minus f of a, but a is 5 in my problem, divided by x minus 5. Now, let's clean this guy up. First off, we want to figure out what f of 5 is. Well, f of 5 means I'm just going to plug 5 into my equation. This would be 5 squared plus 3 times 5 plus 10. Cleaning this up, this is 25 plus 15 plus 10. Let's see here, 25 plus 15 is 40 plus 10 is 50. So I have f of 5 equals 50. So what we have here is this would be equal to the limit as x approaches 5 of f of x minus 50 over x minus 5. So now my derivative would be equal to, now I'm going to replace f of x with the given particular function. And that function is, well, I'm going to take the limit as x approaches 5 of x squared plus 3x plus 10 minus 50 divided by x minus 5. Now we're back to our limit laws. If I plug in 5 right now, I'm going to end up getting 0 divided by 0, so which means I'm going to play algebra on this thing. Well, the first algebra I'm going to play is combined like terms. So this is equal to the limit as x approaches 5 of x squared plus 3x and I've got a 10 minus 50, which makes it minus 40 over x minus 5. Well, to clean this guy up, I believe the trick is going to be factoring. So this is the limit as x approaches 5 of, and I'm going to factor this numerator here, x squared plus 3x minus 40. What times what is 40 that differ by 3 units? I think it's 8 and 5. So this would be, parentheses, x times x, 8 times 5 is 40, and it's a minus, so I want a difference, and the bigger number better be plus. It'll be plus 8 with the minus 5 divided by, in my denominator, is x minus 5. And you'll notice that my x minus 5's cancel, so this leaves me with the limit as x approaches 5 of x plus 8. And notice I wrote limit, limit, limit all the way through the problem until the point where I actually get to plug in the number. When I plug in 5, I don't write limit anymore. 5 plus 8, and 5 plus 8 is equal to 13. So this is telling me that the derivative f prime of 5 is equal to 13, which tells me that my slope of my tangent line, slope of the tangent line when x equals 5 is 13. But that wasn't the question. I used all this work to get in the equation to get the derivative, which is the slope of the tangent line, to be 13. But now I want the equation of the tangent line. To find the equation of the tangent line, we've got to use the point slope formula. Y minus y1 equals m times x minus x1. I got to have a point and a slope. Well, there's my slope. And actually, here's my point. My point is when x is 5, I got 50. So I got the point 5, 50. So I got a point and I got a slope. So I'm going to plug it in. Y minus 50 is equal to 13 times x minus 5. And there's my answer, but I'm going to clean it up and put it in slope-intercept form because it looks better. WebWorks seems to like that. So here we go. I'm going to distribute the 13. This gives me y minus 50 is equal to 13x minus, and 13 times 5 is 65. Now I'm going to add 50 to both sides, solving for y. And this is going to give me y is equal to 13x, and negative 65 plus 50 is a minus 15. And there is my equation of my tangent line at the point 5 of this particular function, x squared plus 3x plus 10. Now, look at part number 2. Part number 2 asks you to find this. Find the derivative of the function using the difference quotient and the definition of derivative. Now, let's go back up here for just a second. If you remember from your college algebra days, this f of x plus h minus f of x all over h is something we call the difference quotient. So you guys have been being prepared for this for many, many years now. This is the difference quotient, f of x plus h minus f of x all over h. What makes it the derivative is when you take the limit as h goes to 0, this gives you the derivative of your function. And it's going to be another function based upon x. And this is what they're after, so this is my definition of derivative. So, writing them down here, f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. A couple of things. First off, what was f of x? Well, they gave me that guy. That was my x squared plus 3x plus 10. What is, if that's the case, what is f of x plus h? F of x plus h means I'm taking x plus h, I'm going to plug in for all my x's. So this would be x plus h squared plus 3 times x plus h plus 10. Classic functional notation. Whatever's inside the parentheses is what I replace x with. So, what I'm going to do is I'm going to take these guys and plug them in into my derivative formula. So this is going to give me f prime of x is equal to the limit as h goes to 0 of x plus h squared plus 3 times x plus h plus 10. Put little parentheses around it because that's my f of x that I'm plugging in. Minus, and very important, put parentheses here, f of x. So let's just copy our f of x function, x squared plus 3x plus 10 all over h. Now, I want to clean this guy up, because right now if I plug in h is 0, this will cancel with this and give me 0 divided by 0. What a surprise. So I'm going to clean this guy up. So this would be equal to the limit as h goes to 0. Now how do I clean this guy up? Now this is x plus h squared. You can't just distribute a power because it's an addition inside. If I want to clean up x plus h squared, I'm going to have to FOIL this guy out, the old first, outer, inner, last. X times x is x squared. X times h is xh. H times x is another xh. That's 2 xh's. Plus h times h is h squared. FOILing this first term out. The 3 I'm going to distribute. This is going to give me plus 3x plus 3h plus 10. Now this negative is going to distribute throughout my f of x function here and change all my signs. This will be minus x squared minus 3x minus 10 all over h. Now if you do this stuff right, half this stuff should cancel. Let's see here, what cancels here? The minus 10 plus 10 cancels. The minus 3x plus 3x cancels. The minus x squared plus x squared cancels. So you are now left with the limit as h goes to 0 of 2xh plus h squared plus 3h. This term, and this term are the only terms left in the numerator divided by h. Now remember, anytime you get that 0 over 0 with all these classic limits, the goal is to cancel. And in this case, we want to cancel that h out. But I got strict multiplication, strict addition. I got addition, a little bit of multiplication there, but I got addition or subtraction typically in my numerator. To be able to cancel this h out, you're going to have to factor. You have to have strict multiplication division to be able to cancel. So I'm going to factor out the h, because I got an h in each term. That would leave me with a 2x plus an h plus a 3 all over h. Now strict multiplication division, now the h's cancel. So this is equal to the limit as h approaches 0 of 2x plus h plus 3. And here we go. Once you cancel out the h's, then you make the limit as h goes to 0. So if h goes to 0, I'm left with 2x plus 3. Therefore, the derivative function of x squared plus 3x plus 10 is equal to 2x plus 3. Now why is this guy so important? Why we like derivative functions? Well, if you look back at the example I did just before this, I did just the simple formula on calculating the slope of a tangent line, which is what this guy does. And it gave it to me, the function, and I ended up getting the slope of the tangent line to be 13. But that only worked when I plugged in 5 originally. If I actually picked a different number, like for example 6 or 10 or -5 or -1 or whatever, and I wanted to know what the slope of the tangent line is, I have to go back and redo all this work all over again. But when you have the derivative formula, all you got to do is figure out what x you want to have and plug it in. Now up here, x was equal to 5. I'll show you. X was equal to 5. So down here, I have f prime of x equals 2x plus 3. Plug in 5. What is f prime of 5? 2 times 5 is 10, plus 3 is 13. And what a surprise. You get the same answer as what we got up here with all this work. But, oh, I made a mistake. I didn't want 5. I wanted -5. So f prime of -5 would be 2 times -5, which is -10, plus 3 would be equal to -7. So if you change your mind, well, I wanted f prime of 0. Well, f prime of 0, 2 times 0 is 0, plus 3 is 3. So the slope of the tangent line would be 3 there. If x was equal to 1, f prime of 1 would be 2 times 1, which is 2, plus 3, which equals 5. So the slope of the tangent line when x equals 1 would be 5. This is very important, so if you want a bunch of different points and you want to know what the slope of the tangent line is, the derivative, once you got the derivative formula, you can just change your mind on whatever x you want and plug it in. Hope this has been helpful, and like I said, your teacher will be going over all this stuff and going in greater detail with all the different kind of problems that you can do with taking the derivative of these things, using the definition derivative, and that will lead us into section 2.2. Again, I hope this has been helpful.